Okay, chapter 6 is areas and volumes. Areas and volumes. Wait, area? We've totally done area, haven't we? How do you find area under a curve, in between the curve and the horizontal axis?
Right.
I love that.
How do you find area?
Definite integral.
A definite integral. So if I was going from like 0 to some sort of, I don't even know what, let's call it b, right?
Yes.
We're going from 0 to b. A definite integral from 0 to b underneath its function f of x would be the area. True?
Yes.
Okay. So why do we have a whole section that's just titled area?
Because it's between curves.
More than one.
Not an accident.
Right? More than one. So now all of a sudden we have some sort of enclosed region that is no longer defined by curve and axis, but curve and curve. Now, it very possibly could be curve and curve and curve, curve and curve and axis and axis. It could be a lot of different things that's closing it in. But it's no longer just a curve and an axis. Gavin and Kyrie, can you whisper a little bit better? Or not talk? So, when we have two different curves, or when we have multiple curves and an axis, we have to find. Okay, so we have these guys up here where area can be between, but then we also have these guys down here. Now, what's the difference in the graphs that you guys can see between square root of x and x squared, square root of x and x squared, and then these guys down here, who, to be honest, he didn't even give us what the function is.
Cosine and sine.
Looks kind of like it, right? Oh, I went off a little bit there. Don't judge too much. What's different?
Well, like, you could the second one, like, passes through the first one instead of, like, being just kind of parallel.
Yeah, and parallel, I get what Adam's saying, but let's just use it in a sense of intersection, right? Can we just use intersections? So, how many times does this first one intersect? Oh, you can't see him? Let's go back up. Let me actually zoom out a little bit.
Like, maybe at the origin.
Once.
Not just once though, right?
Twice.
Twice, because technically, if you plug in x is equal to 0, right?
And why?
At x equals 0, isn't square root of 0 and 0 squared the same thing?
Oh.
But where else or how else does it intersect?
At that point, 1, 1.
Which is at 1, 1, right? So we have the point 1, 1, and we also have the point 0, 0, where they intersect. True? Okay, cool. But what's different with this guy? If I was supposed to find the area between him, just what I see, would that be enough information for me to know what area to find?
No.
I feel like
No.
it's not.
But let's first try to go ahead and write an integral, we can just use, an integral expression for the area between. What do you guys think we could write using an integral that would find the area between square root of x and x squared? What do you think my bounds would be? Let's pause. What do you think what variable do you think we're going to be solving in terms of? X or y? Sure. So if we do dx, why would that be a pretty good guess?
That's what you're thinking.
Your functions are in terms of? Your functions are in terms of x, right? What do you think my bounds would be if I'm using x's? 0 to 1, because that's the beginning of my region. That's the end of my region. Okay, now, I'm going to go ahead and say we need to figure out our integrand. I have little brackets to help us figure out our integrand. Guys, think about that. And if we were drawing rectangles or if we were just shading, what region would the area or the integral of square root of x find us? What would, if we were just to do the square root of x? Where would that area go? Would it be bounded by the curve or would it be bounded by the axis? So if we were to find the area just under square root of x, it would be that entire thing, right? My SAT math people, what happens if we have a larger and we need to get an in-between? What do you almost always need to do? What operation? Subtract. Because we have a bigger area, which is this whole pink one. What's going to happen if I find or if I plug in my function x squared? What area would that be? See it?
Wow.
So if you take the pink, if you subtract the green, what are you going to get left with? The blue that you were originally trying to find anyway, right? So if we take the pink and if we subtract the green, now wait a minute, hold on, but I don't get it. It's all in one big integral. Well, yeah, but what's in between? And how do antiderivatives work when we have addition and subtraction? You just take it piece by piece. So isn't this technically the exact same thing? We're just going to be able to solve it a little bit faster. But isn't it technically the exact same thing as if we were to do this the long way of going from 0 to 1 of the square root of x dx and then subtracting 0 to 1 of x squared? It's technically the same thing, right? It's just written in a much more condensed way, but we're taking the area of the bigger minus the area of the smaller and getting the area in between. What made this really easy? We knew the 0 and we knew the 1 because it was shown to us in the picture. What's going to make this guy harder?
We don't have bounds.
We don't have bounds. Now I could go ahead and, I totally did not have this written in something that you guys could see. Here we go. That was supposed to be an E, and I got distracted somewhere in between. Okay, anyway. So we have natural bounds, which you can see with the intersections, but then you also have given bounds. Now, given bounds, they're going to have to tell you something else. Is there an intersection point of this guy? Yes. But is there a secondary intersection point that we know of? No. So what if I wanted you guys to find this area? How else could I have described? How else could I have described this? I could have said something like, find the area bounded by f of x and g of x for, well, technically I could have also used the y-axis, but let's just make it a little bit easier for x within 0, and let's just call this guy, I don't even know. We'll just call him B. What's the difference? Natural says, I don't know, let me give you two functions and you figure everything out. Given says, no, I'll tell you where to go between. And if they tell you where to go between, all we have to make sure is between 0 and B that there's no weird changing of direction, that there's no weird switch in orientation. So we could say f of x minus g of x. And to be honest, there's a cool thing about area between. Area between will always be positive because they're not caring about who's on top, who's on bottom. They're not caring about a positive versus a negative displacement. They're just trying to literally find good old-fashioned area, which is always a positive number. So then absolute value isn't a big deal if there are no zeros in between. And the zeros of this guy would be the intersections, right? So I'm going to put a quick watch out for f of x equals g of x. And why am I going to do that? Because I'm going to come down here and I'm going to say, so what if B wasn't there? What if B wasn't the intersection? What if B was over here? What would have happened in between? And what happens if you have a 0 and you have absolute value? Do you remember from 2 chapters ago, chapter 4a? You have to solve by splitting it. You have to solve by splitting it up. Anyway, so there, a lot of stuff is coming in this section. I was just trying to give you a big old intro before I lose a few people in like 5 minutes. But what we're doing is we're basically having multiple curves, maybe 2, maybe 3, maybe 4. Maybe they've brought in axes to be little boundaries also. Maybe they've just given you x values, but as soon as they do that, you don't necessarily have a picture in your head, and you might have weird intersections to go looking for. But all of this is going to be solving for different areas. So the purpose of this section is to find the area between two curves. I already talked about that. You might also want to do something about how area between two curves is always going to be positive, which is why we're going to be throwing some absolute values in and watching out for intersections, etc. Usually natural bounds. That's not always, but usually natural bounds. That's what you guys just saw on the page before. I think I made those the orange ones. Usually natural bounds. And so we just look for the intersections. We find the intersections. And remember, to find the intersections, we just solve for where f is equal to g. We have other things, so I'll think about that too. but sometimes you're going to have defined bounds. Now that's super sad. X equals B just kind of popped on the next line. Let's get him back up where he's supposed to be. Now, they could actually say from x equals a to x equals b. Remember, they could also put that in interval notation like I just did. X is within a to b. Or they could also give you some sort of picture where they're like, hey, can you please find this area between, and you're going to have to figure out who is A, who is B from the picture. So there are a couple different ways of doing it. Actually using words, actually using intervals, or actually giving you a picture and you have to figure out A to B. But we've already had some practice with the picture just because you guys were dealing with good old-fashioned, just plain old area between the curve and the axis back when we first learned intervals. But these steps, well, these steps are basically helping us know how to set up an interval. We're going to be subtracting almost every time in some way, shape, or form. We're going to be subtracting in some way, shape, or form. The hardest part is going to be probably 2 and 3. In that, number 1 says I have to figure out who is most positive, highest, or farthest to put first. In my subtraction. Or I could just use absolute values and say, I don't really care. I could figure out who's the highest, who's the most right. I could figure out who's the most positive. Or I could just use absolute value and be like, it's all right, it'll work out. But if I use absolute value, I especially have to watch out for number 3. But even if I'm using a picture and if I'm like, this guy's on top or this guy's most positive, aka farthest right, well, you have to keep looking at the picture and make sure that nothing ever switches. Even if you have a picture, this might not be the same thing the whole entire time. So the absolute value kind of helps us because then we have to realize, we have to split up. So a quick reminder that we need to split up at intersections. Now technically, we always split up at zeros, but zeros are going to be the intersections because if we have f of x minus g of x, that will equal 0 at the places where f is g. So that just kind of, I don't know. I say intersections because the zeros are going to be the intersections since we have 2 different people who are involved, 2 different functions. Not just f, but f and g. And that gives you, basically, for those of you guys that are going to have to be taken off, that gives you the setup as to what we're going to be doing today. We're going to have functions. We're going to take them off to the side and say, hey, do you guys have intersections? Good old-fashioned pre-cal. Ooh, when we solved systems of equations, it was helpful. Intersections. Sometimes it's only possible on a calculator because it's going to be decimals. Sometimes we can do it by hand with things like factoring. If we take something like x squared equaling to x cubed, without even a picture, we could go ahead and maybe do some factoring to help us out. All right, kiddos, going on the field trip. It's time for you to go. Love you, be safe, have fun. If I were you, get the examples before you come tomorrow. But for those of us that are doing our pre-cal, we're setting them equal to each other, trying to find our intersections, and there are how many of them? 2. Which means they only intersect at 0 and at 1. Wait a minute, how did I know it was here? How did I know it was 0, 0 and not 0, 5, 0, negative 2, 0, something else, something else, something else? Yeah, why not just set x equal to 0, right? What happens if I set x equal to 1? Oh. Is this exactly like the picture that we just did? Nope. Why? Well, yeah, don't you know who this guy is? Isn't he the one that goes like, swoop, there he is, right? And isn't this guy the guy who goes, swoop, wait, how do these intersect? If I plug in 1/2 squared, isn't it 1/4? What if I plug in 1/2 cubed?
1/8.
What's the cube do for just a little bit?
Wow, that's a really small.
But how did I know that? Well, because the math tells me it intersects twice. And I know that 2 cubed, 4 cubed, 5 cubed are all higher than 2 squared, 5 squared, 10 squared. Bye guys, thanks for taking the time. So I know that cubed goes higher eventually, but for just a little bit. 1/2 squared is 1/4, 1/2 cubed is 1/8. For just a little bit, 1/8 is actually lower. Or sorry, x cubed is actually lower. So then how would I find the area between? If I was to be all snazzy and be like, I can see the picture, I know what's going on, I could go ahead and say area is equal to the integral from 0 to 1 of who's on top? Who's going to be higher values, bigger area? Yeah. Who's going to be the lower guy? And that's me just basically looking at it and saying, I know who's going to be the positive guy. I know who's going to be the negative guy. So I'm putting them in the proper, check it, number 1, the proper order of the bigger minus the smaller. Just like you would do in an SAT problem if you were supposed to find like the area in between, like a circle and a rectangle, square, whatever. Had to be a square, or else it wouldn't be possible to be a circle. Circles should technically hit. You guys know what I'm talking about. But wouldn't you do the square minus the circle, not the circle minus the square? You do the bigger minus the smaller. Aw, they're all waiting. They're going to miss this so Okay.
That's so mean.
Wait, who?
Ruth. Ruth had barely made it on.
We all know they have their banter thing. Okay, so coming back. But what's the other way that we could have written this? We could have started at the very beginning, gotten our intersections, and then just said, I don't care. He looks nice. He looks nice. And let's just do that. Are they going to be the same thing?
Yeah.
Are you sure? But this one is so much harder, because this one I had to ask myself, are there any intersections in between? We already found the intersections. There aren't any more. Oh, cool. So we can just throw out the absolute value, and we can do x cubed. Well, wait a minute. You guys know these antiderivatives, don't you? Not throw out, but throw out as in, okay, I'll show it.
Bye-bye.
We're allowed to pull out the absolute value only if we've made sure there are no intersections, no zeros, no places where they equal each other in between the values.
Oh.
So then I go ahead and say,
What's the difference between having them on one side and having them on the opposite?
well, in this one, none. I shouldn't say none. In this one, no changes need to occur. We didn't need to split them up. In other ones, we need to split them up because if we were to do a subtraction one way, we would get a positive, and the other one would be a negative, and it would take away from each other before I ever absolute value, as opposed to like displacement, where I need, or total distance traveled, where I need this amount, positive, this amount, positive, this amount, positive, and I'll get all my area added together. Trust me for now until we see a picture. Because this one's an easy one. Meaning, if I subtract the wrong way, all I'm going to do is just get a negative, and I can flip it to make it positive, which is what I'm doing right now. I put it in the wrong way on purpose. I'm like, I don't know, I picked one. Minus, I picked another one. And if I go ahead and plug in, I end up with 1/4 minus 1/3 f of b minus 0 minus 0 f of a, absolute value. When you subtract 3/12 minus 4/12, don't you get negative 1/12? Oh, I did it the wrong way because I needed absolute value of that, which is positive 1/12. But if I, what just happened and why did it happen?
Where'd you go?
I don't know.
I miss you so.
Okay, I don't know why everything just changed. I'm just going to leave
Enjoy
that as
yourself.
it is.
Enjoy yourself.
Misty, what did you factor out to make it 1/4?
Ah, what disappeared? What did I do?
You ended right.
I anti-derived. Check it. So I did x to the 4th over 4 and x cubed over, I took the, yeah. Sorry, so then that would be, let's see if I don't mess everything up this time. That'd be the absolute value of 1/4 minus 1/3, plugging in 1, minus 0, plugging in 0, which equals the absolute value of negative 1/12. Oh, I chose the wrong way. No big deal, it's 1/12. Okay.
And I
This one could be like, I knew what the picture was. I took all the time to graph it. I'm going to get a positive answer the first time. So,
Nice. And yet, who cares?
exactly. Do you see it?
I like it. I bought it.
What?
Like my hair? Just bought
Question. Does it end up being the same thing?
it.
Yes.
Wow.
But which integral is technically trickier? Just looking at it.
Toward the bottom.
This one's trickier because this one has absolute value, right?
Yep.
So this one is, ready?
Absolute value.
Easier to make,
Harder to do.
but easier
To fail.
to mess up.
Oh, wow.
Same thing.
What is? Because I didn't need a picture for this one. I just said, whatever, subtract them and throw in absolute value. But why is it easier to mess up? Because in a more complicated function, if I don't split up based on any possible intersections in between, I'm going to have a very different wrong answer. You always try to split them up. Why didn't I split this one up? Why was I able to pull it strictly out? Were there any places to split up in between the bounds?
No.
It was already split up by the bounds, so I was done.
Oh.
Don't worry. I'm basically preparing you for harder examples that haven't come yet.
Is that?
Oh, it's a forever card.
Yes, it's all.
My artistic ones, you get to have fun. Hey, and you have pictures drawn on all of these, which means we just get to write them. And yes, it should go in your forever card.
So, Misty, we're having 8 forevers in this chapter?
What?
Yeah, wait.
I almost did.
I was asking a question.
Why did you try this?
I'm freezing the screen for you guys to get your forever and for me to go peek at where we're headed. Kyrie, can you go check my box in the office? Thank you, thank you. I'm hoping they have copies for me.
You're a senior.
Wait a minute, guys. This isn't number 40.
43.
Okay.
We only have 7. Do you remember my dilemma from like our second forever card? How I
Yeah.
wrote it and I skipped the page because it was so stuck together.
Yeah.
And then I had to rip it out and now I only have 49 cards. So I don't know what I'm
The same amount of days you have left to school.
Yeah. Poor guy. I think we'll be okay though.
Why am I waking up?
I think we'll be okay. We're gonna have 1, 2, 3, 4 different cards. So we might actually have that extra. Thank you. Might have that extra that we need.
Yeah, I'll say no.
So number 43, you guys got?
Almost.
Do you guys realize that really this is just another application of antiderivatives or integrals?
Yeah.
Right? Because, where's my marker? Oh, I lost it. Here you go. If you have a picture, couldn't you, this is x equals 4 by the way, couldn't you set up and be like, hey, I'm going from 0 to 4, and if you see the picture, you can go ahead and like, aha, and then, aha. What do you think you need to do to solve it? Practice integrals. Ooh, definite integrals too. But what's going to happen if it changes instead of x's having y's?
Why having a what? Wait, is that right?
Joe's having Joe.
Is it possible to do a dy and to
Yeah.
do a
Yeah.
f of y minus g of y with y bounds?
Yeah.
Yeah, it is. But do you guys see that we're going to have to still do integrals a lot? Tomorrow, bring your calculators. Tomorrow, bring your integration brains, and we'll keep going. Bye, guys.
Can I bring my brain?
If I were you, I would watch. The reason I screenshotted an online tutor do some area between examples tonight. But you get to choose. Do you choose Khan? Do you choose Patrick? Do you